We're going to now talk about the math of counting. How do we count large quantities? So let's start by just doing an example. Let's say a coin is tossed 3 times. In how many ways can the result occur? So one way we can count is just by brute force, by making either a list, or what I'm going to do is actually make a tree to describe all the possibilities. So first coin toss, there's 2 options. It could be either heads or tails. Then for the second coin toss, if I get heads for the first one, I still have the option of heads or tails. The same is true if I get tails for my first coin toss. When I throw it again, I still have those 2 options, heads or tails. And then finally, for that third coin toss, for each of these possibilities, when you throw that coin the third time, you still have a possibility of heads or tails. And each one of these branches in this tree represents a different possible outcome. So for example, in pink, that would represent the outcome, I got heads, heads, heads. And then in blue, that would be the outcome, heads, heads, tails. And we could continue. Each one of these branches is a different outcome. And we can just go through and count how many branches do we have? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 different ways the results can occur. So a tree is a really nice way to visualize how a series of events can occur, like tossing this coin 3 times. But it turns out we actually have a faster way that we can solve this problem. There's something called the fundamental counting principle. And this basically says if we have a series of tasks, we can multiply the number of ways each part, each thing can happen together. So this is easier for me to explain with an example. Let's go back to that first problem. We toss a coin 3 times. So one way we can get the answer, how many outcomes are there, is we can break this down into 3 different things. First toss, there's 2 different possibilities. We could get heads or tails. Second coin toss, again, there's 2 possibilities. We could get heads or tails. And the same is true for the third toss. There's 2 possibilities. This fundamental counting principle says we can multiply those numbers together. 2 times 2 times 2. That gives us 8. So there are 8 different ways that this can happen. 8 different outcomes when we toss a coin 3 times. So notice we got the exact same answer. That's a nice thing. All right, let's do a couple more examples. Example 2, in a dinner special, you choose one of 3 appetizers, one of 6 entrees, and one of 4 desserts. How many different meals are possible? So again, we've got 3 things happening here. You get to choose an appetizer, an entree, and a dessert. There's 3 possibilities for the appetizer, 6 possibilities for the entree, and 4 for the dessert. Our fundamental counting principle says we can just multiply those numbers together. I got 72 when I did that. So there's 72 different meals that are possible. All right, here's one more example. In how many ways can a president, vice president, and secretary be chosen from a club of 25 students? All right, so it's 3 things still. We're going to choose a president, a vice president, and a secretary. So if we pick our president first, there's 25 different options. We can pick any of the 25 students. But when we move on to vice president, we have to pick someone different. We can't repeat people, right? If I choose Anne to be president, she can't also be vice president. We've already picked our president. So for vice president, we only have 24 choices. And then for secretary, again, we can't pick the same people we've already chosen for president and vice president. We're going to say repetition is not allowed. Repetition of people is not allowed here. So there are now 23 options. I can multiply these together. I got 13,800. So that's the total number of ways I can pick those 3 positions. Now, technically in that last example, this one with the president, vice president, and secretary, we've actually done something called computing a permutation, and I want to define the idea of permutations and combinations to help us with some of our counting problems. So a lot on the screen right now, but basically a permutation is when you want to pick R items from a set of N items. So in the previous example, we wanted to pick 3 people out of a group of 25. Okay, so we were choosing a president, vice president, secretary, so 3 different people from a total of 25. With a permutation, we also assume that order is important. And so what I mean by that is if I choose Ann to be president and Bob to be vice president, that is different than choosing Bob to be president and Ann to be vice president. So, for example, in the previous problem where we said, in how many ways can a president, vice president, and secretary be chosen from a club of 25 students? Using this permutation notation, we would write that as 25p3 because we are picking 3 people from a class of 25, from a group of 25. So here's our formula to compute permutations. This NPR, or picking R out of N items, our formula is, I'm going to read it as N factorial, that's what that exclamation point means, divided by N minus 1 factorial. So first I need to define the idea of a factorial. There's the definition of a factorial. N factorial, you take N times N minus 1 times N minus 2, etc., all the way down until you get to 1. So for example, 4 factorial means you take 4 times 3 times 2 times 1. You get 24. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. And that's 720. So that's what a factorial is. You just multiply all the numbers below that number together, and that's what we mean by that operation, factorial. So for example, if I wanted to use this formula to compute my permutations of picking 3 out of 25 items, the formula says we take the n, the first number, so 25 factorial, and we divide that by 25 minus 3 factorial. 25 minus 3 is 22. So this formula says the answer would be 25 factorial divided by 22 factorial. Now to do this computation, it's helpful to simplify because I don't want to actually do 25 times 24 times 23, etc., all the way down to 1. Not only is that going to be time consuming, but that's a really, really big number, and I might actually get some issues in my calculator. My calculator may not be able to handle such a big number. So there is a nice way we can simplify this. So 25 factorial, again, it means we're taking 25 times 24 times 23, etc., all the way down to 1. And 22 factorial means we're doing 22 times 21 times 20, etc. And so notice what we can do here. We can actually cancel the common factors, the 22, 21, 20, 19, etc., all the way down to 1. So we can cancel the 22 factorial out, and we're just left with the 25 times 24 times 23. And notice that's exactly what we did to compute this problem in the previous section. So let's compute some other permutations using our formula. So 10p4 means we are picking 4 items out of a group of 10. So using my formula, I would take 10 factorial divided by 10 minus 4, which is 6 factorial. We can cancel the 6 factorial out, and it leaves us with all the numbers that are bigger than 6. So I did that canceling in my head, but basically, when you're canceling that 6 factorial out, it's canceling out all the numbers from 6 and down, and so you're just left with 10 times 9 times 8 times 7. That's 5,040. Okay, what about 30p2? That would be 30 factorial divided by 30 minus 2 factorial. So 30 factorial divided by 28 factorial. And then when I do the canceling, what happens is I get rid of all the numbers from 28 down. So I'm only left with the 30 and the 29. So 28 and below is all gone. So I'm just left with 30 times 29, which is 870. All right, so let's solve a problem using permutations, and then let's introduce our last concept in this video. So my example says, in how many ways can a first prize and a second prize be given to 30 contestants? So we'll answer that question first, and then we'll deal with the second question. So in how many ways can a first and second prize, so we're picking 2 people, be given to 30 contestants? So picking 2 people out of a group of 30. So that would be 30p2. I did this computation already on the previous slide, 30p2, so I won't do the work again, but I ended up getting 870. So there's 870 different ways that I can give a first prize and a second prize, so pick 2 people out of a group of 30 to win prizes. Now, what if I change the question to, in how many ways can 2 identical prizes be given to 30 contestants? So, the thing to notice here is in the first part of this problem, when we're giving first place and second place, order matters, right? If I give Alice first place and Bob second place, and I give Bob's first place and Alice second place, those are 2 different options. Those are 2 different things. And so we say order here matters. Whether you pick A first or B first actually matters because the prizes are different. With permutations, we are counting assuming that order matters, and we're thinking of these as 2 separate options. But when we get to that second question, what if we have 2 identical prizes? Now all of a sudden order doesn't matter. It doesn't matter who I pick first or second because the prizes are the same. And so when order is not important, we call what we are counting a combination. So here's my notation. We use C. And so NCR stands for the number of combinations, so the number of ways you can pick R things out of a group of N when order doesn't matter. So if we want to answer the question, in how many ways can 2 identical prizes be given, we're actually going to compute 30C2. So how many combinations of 2 things out of that group of 30 are there? So just again to emphasize, we're saying order doesn't matter, so we want to count giving the prizes to A and B as the same thing as giving the prizes to B and A. And so here's my formula for combinations. It's really similar to my permutations formula with one difference. We just have this extra R factorial on the bottom. So if I want to compute 30C2 using my formula, I would take 30 factorial and divide it by 2 factorial times 30 minus 2 factorial, which is 28 factorial. And then I'm going to do the same kind of math I do with my permutations. I'm going to try to reduce or cancel out that 28 factorial. So that's going to cancel out all the numbers from 28 down. And so I'm just left with on the top the 30 times 29. Again, 28 down, all got canceled with that 28 factorial. And then I still have the 2 factorial on the bottom. So 30 times 29 is 870, and then 2 factorial would be 2 times 1, or 2, and so I got 435 as my answer. 435 different ways. All right, so for my last kind of set of examples, I just want to run through 3 problems and first think about whether each situation is an example of a permutation or a combination. So again, permutation means the order that you pick the people or the objects in matters, and combination means the order doesn't matter. All right, so first example, in how many ways can 4 students be chosen to represent their class of 50 in a school board meeting? So the first thing we have to think about is, does order matter? And in this case, order doesn't matter. The 4 students all kind of have the same standing. Doesn't matter what order we choose them in, they're all going to go to the school board meeting. So we are picking 4 out of 50. Order does not matter, so that would be combinations. So I'm picking 4 out of 50, so that's going to be 50 factorial divided by 4 factorial, and then 50 minus 4 is 46, so that's where that 46 factorial came from. To do this computation, I'm going to cancel, I'm going to get rid of that 46 factorial, and that's going to get rid of, on the top, all of the numbers from 46 down. So I'm just left with the 50 times 49 times 48 times 47. 46 and down is gone. I got rid of my 46 factorial, and then on the bottom I still have the 4 factorial. So 4 times 3 times 2 times 1. I'm going to put this into my calculator, and I ended up getting 230,300. All right, question 2. In how many ways can gold, silver, and bronze medals be given to 12 skiers? So our first question is, does order matter? And the answer is yes here. It's different if you win gold versus silver versus bronze. Those are different options. So this would be permutations. We are picking three medals out of a group of 12 people. So I'm going to use my permutation formula. I get 12 factorial divided by 12 minus 3 is 9. So divided by 9 factorial. That leaves me with 12 times 11 times 10, and everything from 9 down canceled out. So I got 1,320 options. All right, finally, last example. In how many ways can we pick 3 desserts from a menu of 15 options to serve at a party? So does order matter? No, it doesn't matter. We're still picking 3 desserts. Doesn't matter what order we pick them in. So this is combinations. We're picking 3 out of 15. So using my combinations formula, I get 15 factorial divided by 3 factorial, and then 15 minus 3 is 12. So there's a 12 factorial in the bottom as well. We cancel the 12 factorial out, and that just leaves me on the top with 15 times 14 times 13. The bottom is 3 times 2 times 1. Put that into my calculator, and I got 455.